We are going to be talking about prisms. A prism is called a solid. Solids are three-dimensional. Anything that is three-dimensional is called a solid. A prism is a solid that has two parallel, congruent, polygonal bases. So if I want to draw a prism, I usually start with drawing the bases. I can draw a hexagonal prism by drawing a hexagon that's kind of flattened so that you can think of it as being three-dimensional. Something that's three-dimensional and tipped up a little bit looks flattened, right? Then if I want to continue drawing this prism, I'm going to draw these sides down. But I want the base to also be hexagonal. I usually just draw the front edge, unless I want to show that, hey, this is three-dimensional. So let me make these sides that are in the back dotted, and then you can see that we have something that is three-dimensional. You can see the process then of drawing a prism. Also, along with this, we name a prism by its base. So this is a hexagonal prism. We could talk about a square or a rectangular prism. Rectangular prism would have a base that is a rectangle. And again, because we're drawing something three-dimensional, a rectangle, when you tip it up or flatten it, looks like a parallelogram, doesn't it? So this right here is a rectangular prism or a box. And again, if you want to make it look three-dimensional, you can draw the edges that you cannot see because they are behind with a dotted line. I have to come this way, I think, to draw that dotted line. We could have a trapezoidal prism, and then you have the base is a trapezoid. Making it 3D, so dotting these other edges in. We could have a pentagonal prism, yes, and then we have pentagons on the bases. We could have a triangular prism with triangles on the bases. Okay, you can see that so far what I've drawn here are called right prisms or orthogonal prisms. These are all right prisms. We could also draw an oblique prism. An oblique prism is when the bases aren't directly above each other. They're still parallel and congruent, but you've taken them and slid them so that the bases are not right above each other, which means because these bases are right above each other, all of these angles right here are going to be right angles. But if you take these two bases and slide them so that you have one hexagon that is here and another hexagon, let me clone this, that is off at an angle, and then you draw the edges, then you are forming an oblique prism. Your bases are still parallel and congruent, but they're not one above each other. Most of the prisms we're going to be looking at, fact is all of them, besides the fact that we mentioned that there are such a thing as an oblique prism, all of the prisms we're going to be looking at are right prisms. So when we give a theorem as to how you find the volume or how you find the surface area or whatever, it's of a right prism.
What is that?
Oblique, O-B-L-I-Q-U-E. It's just nice to know that word. But we don't work with oblique prisms. Now, for each of these prisms, we have the bases. The base is always the side that's parallel and congruent and is not always rectangular. The base is those parallel and congruent surfaces that are directly one above each other. Then we have our lateral surfaces. The lateral surfaces are always rectangles on these right prisms. They are the rectangles that form the walls. And in this case, we have the vertical surfaces. Or lateral surfaces. Can you picture each of these boxes, you might say, as a room with a floor and a ceiling and walls? You could almost picture a person standing in there, right? It's like a room. Okay? The lateral surfaces are the walls. We can think of this room right here as a prism. Fact is, that's where the application for all of this comes. It's finding... No, it really is not. Not because of that little doorway that's there, but because the ceiling is not parallel to the floor. It's okay for a prism to have a strange-shaped base. It's still a polygon if the base of the prism does something like this. So you come along and you go straight for a while, and then there's a little jog, and go back out and come along and straight for a while, and then you come back like that. It's still a prism if that is the shape of your base. And I'm trying to draw so it looks like a box that has that strange jog in it, right? Let me erase that piece. Oops. Okay, I didn't do a very good job. But still, you could draw those dotted in, make it look three-dimensional. Hope it goes back like that, and then like that, and then like this, and like that. And it comes back here, and then comes right there. And you could show it like that. It's still a prism. Because the bases are still polygons, and they're still parallel. It's just a strange-shaped base. Okay?
Does that say more the vertical surface?
Or the walls. The lateral surfaces are the walls. Okay. Now, when we find the volume then of a prism, we can use what we learned to help us find the volume of this strange-shaped prism, or the volume of this room,
Or the chair?
or the volume of anything that takes up region of the room, you might say.
That post,
The poster
the smartboard.
is not three-dimensional though.
The smartboard is.
The smartboard is. It has a thickness. It is a rectangular prism. And we could talk about, if we had a box this size, how much sand would it contain?
Not much.
If we filled it with sand.
A lot, actually.
Okay? And that's volume. Volume is how much would it contain if you filled it. How much water would... You can make an aquarium that's the size of this smartboard. And then how much... Well, you could have little fish in there. And then you could think, how much water do you need for your aquarium? And then how much chemical do you need to put in that water? Because it depends on the volume of the water or whatever, you know. Okay. So on. So a right prism has base and it has lateral surfaces. Those are the surfaces. But you have edges as well. A right prism has base edges. Now the base edges are the edges that go around the base. So right prism has base edges. Those are the edges that go around the base. We could say edges that form the sides of the base. That might work. Edges that form the sides of the base. And then there are lateral edges. The lateral edges are the vertical edges. The lateral edges of this same figure are only these edges right here. They are the edges that are vertical. Okay? So the base edges would include the edges of each base. The base edges are blue. The lateral edges are green. So lateral edges
Is that lateral?
lateral, L-A-T-E-R-A-L. Those are the edges that are vertical. I guess the base edges we could call the horizontal edges. Now, because a solid can be tipped on its side, sometimes these lateral edges will not be the vertical edges, right? Like you can picture this figure right here. Let's group everything. Okay, that didn't work very well. But you can picture this figure right here. Quickly redrawing it. As being tipped on its side. And when you do that, you still have this base as a hexagon. Because your bases have to be parallel and congruent. Your lateral surfaces are always going to be rectangles. So even when you tip this on its side, the bases are called the hexagons, or the hexagons are called the bases. Okay? So your bases have to be parallel, congruent surfaces that are polygons. The lateral surfaces are rectangles, and they usually form vertical walls. But if you tip it on its side, it's still the lateral surfaces that are the rectangles, and the bases that are those congruent parallel polygons. Okay. Here's another example of a strange-shaped prism. If you have a floor that you're using I-beams to support, the beam looks like an I. That's why it's called an I-beam. And it runs my I-beam is twisting. Okay? Your surfaces that are the bases are the I shape. The lateral surfaces are these rectangles that go around the edge. That is still a prism. And you can find its volume or its surface area. The same way that we're going to talk about how do we find the volume and surface area of, say, this prism right here, or any of those prisms. Okay. So now, moving past the vocabulary to how do we find volume and surface area. You know, I didn't talk about the vertices. I forget sometimes about all the vocabulary that goes with this. But where any two edges come together, that point where they meet is a vertex of the polygon. Okay? So where your edges come together and form points, you are getting the vertices of the polygon. Not of the polygon. Polygon, yes, but also of the prism. Next piece. Theorem 12.1. We have the lateral area of a right prism equals the perimeter of the base times the height of the prism. Right. So here what we have to do to picture why this is we have to be able to take that hexagonal prism that we had drawn up there and cut the lateral surface in our mind and roll it out. And when we do that, if we take this hexagonal prism and slice it right there, and roll out the, you might say the pattern for making it, then you would have, these two hexagons would fold up and fold down, so you would have these hexagons, and I'm not drawing a hexagon, let me try to draw a hexagon. And you would have these lateral surfaces, but the lateral surfaces would all be folded out this way. And since we have 6 of those lateral surfaces, that's 4. Let's do a couple out this way. 5, 6. And you could picture that you could actually fold these bases down and wrap the surface around it. So we have 2 base areas, which are capital B, that represents the base area. And then we have this lateral area. You can see that that lateral area would be like a rectangle with these 2 dimensions. The 2 dimensions of the lateral area are the base of the rectangle and the height of the rectangle. How would I find the length of the base of the rectangle? Well, that is in fact the distance around this hexagon, because those are in fact going to be wrapped around that hexagon. So the area of the lateral area, capital L, capital A, lateral area, is going to be the perimeter of the base times the height, which is this distance right here. This is our height, which is the same as the height of the prism. So the perimeter of the base times the height. Now when you're working with the prism, your lateral edge is the same length as your height. The height is the lateral edge length. So your lateral area then put into variables is P times H, where P is the perimeter of the base and H is the height of the prism. Lateral area. Will be the perimeter of the base times the height of the prism. Now theorem 12.2, which is our volume. Theorem 12.2, the volume of a right prism equals the area of the base times the height of the prism. So if we want to find the volume of a rectangular prism, it's easiest to understand this formula looking at a rectangular prism. Because we can actually picture a rectangular prism as being formed with little cubes. If, for example, the dimensions of the base of this is 5 by 2, and the height is 3, if we were working with, say, feet, we'll make it be feet so that we can talk about units. The fact that this is 5 feet means that we can actually have 5 vertical strips 1 foot wide. The fact that this is 2 feet means we could actually have 2 vertical strips 1 foot wide. And then this being 3 feet means we could actually have 3 horizontal strips 1 foot wide. Now if you start thinking about what does this do to the box, it's going to divide the box into little cubes. Little cubes that each have 1 foot by 1 foot by 1 foot. Now the base itself is made up of how many little cubes? How did you find it? It is, because it's 2 this way, right? and 5 that way. So there are 10 cubes in the base itself. Then, how many layers of 10 cubes do we have? 3 layers, which means how many total cubes are going to be in that? So we're going to have 10 times 3, because there's 10 in each layer and there are 3 layers, which gives us 30 cubic feet. When you go feet with a little exponent of 3, it means you are working with a cube that's 1 foot by 1 foot by 1 foot. So when you say cubic feet, it means you're actually working with little cubes that are 1 foot by 1 foot by 1 foot. A cubic foot. Now, in general then, you can find the volume of a right prism by taking the area of the base times the height. Because the area base is how many cubes are on the base level, and the height is how many levels. In variable form, this is V equals a capital B is always the area of the base. A lowercase h is your height. So when you see a capital B, it means you have found the area of the base. V is volume. Okay. We need to talk about total surface area now. We have here 2 formulas for our prism. We have the lateral area is the perimeter of the base times the height. We have the volume is the area of the base times the height. The total area is your lateral area plus the area of the 2 bases, because it is your total area. And if you're talking lateral area, you're only talking about the area of this lateral surface. So total area is that area plus the 2 base areas. So lateral area plus 2 base areas.